Our topic for this week is how we measure stars. And we're going to start by talking about some fairly basic stuff, some of it is revision. First of all, we have the idea of trigonometric parallax. We've already covered this. Basically, this is how we're going to measure the distance to our stars. That's one of the parameters we're going to need to understand our stars. And so we're using the baseline of the Earth's distance from the Sun to measure the distance to stars using trigonometry. So here I've got the difference in position in the sky of a nearby star compared to the background stars moves by an angle of 2p from seeing it in January to seeing it in July. And so it's moved by an angle of 2p, and that means that the angle p, the tan of it, gives us the distance where this opposite side is 1 AU. Now, if p is very small and we measure it in radians, then tan p is approximately p, so we can just say that p is 1 AU over the distance. So we get the distance in AU, and but that's if p is in radians, which is a very big measure if you're working on the sort of angle we're talking about. So we're going to convert this to arc seconds. So 1 radian is approximately 180 degrees divided by pi. In fact, it's exactly 180 degrees divided by pi. And so if we want to do it in arc seconds, we have to put in the 180 times 3600 for how many arc seconds there are in a degree, divide by pi, which gives us the 206,265 AU. So we've got a distance of 206,265 AU for 1 parsec, and 1 parsec is then 3 times 10 to the 16 meters. Now here you can see the difference between a close by and a further away star. Remember that the parallax angle is half the apparent shift over 6 months, and we get this where if p is the angle in arc seconds, then d is the distance in parsecs, and the nearest star is Proxima Centauri, and it has a shift of 0.77 arc seconds, very, very small, cannot detect it with the naked eye. That gives it a distance of 1 over 0.77 or 1.3 parsecs. Now, we'll come back to that idea later, but the other thing that we want to know about is that stars actually move. We know that we're moving through the galaxy, so do all other stars. So they appear to be fixed, but it's just that they're at a very large distance. And so if we've got stars that are, like for instance here, we've got the Alpha Centauri system. These are the closest stars to us, and they're moving at some speed through space relative to us, and it's actually along this red line. From our perspective, we will see a transverse across the sky motion and a radial motion. So you have what's the tangential motion. Transverse motion is across the line of sight. That's something that we should actually be able to measure if there's any significant motion over the course of a few years, and this is called proper motion. And then we also have this line of sight direction, the radial direction, and that's measured using the Doppler effect. And if we use both, we just use Pythagoras, so we've got that the actual motion of the star is the tangential and the radial combined. If we look at something like the Big Dipper here, you can see that the motions of these stars, these three are moving that way, this one's moving that way, but these are moving in completely the opposite direction. And if we actually work out what it looked like in a few million years, maybe even a few 100,000 years, you've got them completely stretched out into a different shape. Okay, so that's just some basics that it's useful to know about, but one of the most important things that we need to know about is that we have stars of different brightnesses, and we need to be able to assess what that looks like. If we look up at the sky at night, it's got all these different stars of different brightnesses, and this is something that man's always been able to observe. And so about 2,000 years ago, Hipparchus basically said, I'm going to divide all the stars I can see into different brightnesses, and I'm going to call it magnitudes. And I've got the brightest stars are going to be the first magnitude, and the faintest stars are going to be the sixth magnitude, and I'm just going to divide them according to how bright they look to my eye. And it's based on how the eye perceives light, and we call these apparent magnitudes. So originally this was based on the idea of the celestial sphere, so all the stars were at the same distance. Now we understand that there are different distances, so their magnitude is an apparent thing that's a combination of their true brightness and their distance from us. And the important thing to note is that since the brightest stars are the first magnitude and the faintest stars are the sixth, the higher the number, the lower the brightness. The brighter the star, the lower the number of the magnitude. So we have, if you want to get brighter, you have to make the magnitude go down. Okay, so like I say, Hipparchus had this magnitude scale and it was based on his visual observations, but when we measure brightness with a real instrument, we're measuring photons per second spread over a certain area. We're actually measuring how much energy passes through a certain surface within a certain time. The eye does not behave in a linear way. It has a logarithmic response to light. And so if we actually measure the brightness from these stars, we can compare it to the eyes and do a conversion between this ancient magnitude scale and a more measurable scale. And so what we've got here is that we found that the difference between the first magnitude stars, the brightest stars and the faintest stars, was basically about a factor of 100 in brightness. So even though they appear to be only 5 times less bright for the sixth magnitude, they're actually 100 times less bright. But it's to do with the way our eyes perceive the light. And so we could quantify this. And the way that we did it was to say, okay, we're going to find the very faintest star that we can detect with the naked eye, and we're going to call that one a magnitude 6. That's our anchor. That's where we set it. And then we're going to say that it's the first magnitude star, a star with a magnitude of 1, is exactly 100 times brighter. And because it's this logarithmic scale, what we get is that then we need to divide it into 5 units. So we have that the first magnitude star is 100 to the 5th times brighter than the second magnitude star. And the second magnitude star is 100 to the 5th times brighter than the third magnitude star, and so on. So then your first magnitude star is 100 to the 2/5 brighter than the third magnitude, and your fifth magnitude star is 100 to the 4th less bright than the first magnitude star, and so on. And so that if following this pattern, the sixth magnitude star, first magnitude star is 5 over 5, so 100 times brighter than the sixth magnitude star. So this is the proper quantification of magnitude based on how we measure brightnesses in energy per unit area per second. So if we look at this, it means that if we've got a magnitude difference of 1, then the actual difference in brightness is 2.512. So this is the 5th root of 100. So if you do 2.512 to the 5, you get 100. And you can see that, so here we've got, if we've got a magnitude difference of 5, 2.512 to the 5 gives us a magnitude difference of 100. A brightness difference of 100. And so you can work out that if you've got a magnitude difference of 10, then it's 2.512 to the 10, it's 10,000 times brighter, and so on. And so we can use this as a conversion. I want to put this in perspective for you. Here we have a scale of brighter to dimmer, and remember that the more negative the brighter it is, the more positive the fainter it is. Something like Sirius, which is the brightest star in the sky, now has a magnitude of minus 1.4. It would have had a magnitude of 1, but remember that this was based on the eye's perception and there were only 5 units, and Sirius wouldn't have been up that much in Greece, so it's something that may not have been paid that much attention to. And now we're quantifying it, so we're basically taking that specific quantification where 6 is exactly the faintest, and 100 times brighter would be this would be a first magnitude. So this is actually 2.4 magnitudes brighter, and so it actually is even a lot more bright compared to the faintest stars. But something like Venus is even brighter. This is the first thing that appears when it's up in the sky at night, and it's minus 4.4, so it's at its brightest. It varies in brightness because it varies in distance from us. Likewise, the full moon. The full moon also varies in brightness, not by much. Has a magnitude of minus 12.6. That's really bright. And then the sun, because it's so close to us, is incredibly bright and has this magnitude of minus 26.7. Here we have the naked eye limit. It's at 6. If you have binoculars, you can see out to a magnitude of 10. And so that means that this is going to be 4 magnitudes fainter, or several thousand times less bright that you can see. But you can see here Pluto has a magnitude of 15.1. Well, that means that even with binoculars you can't see it. If you get to a large telescope, you can see out to about 21, plus 21. And if you've got a very large telescope, or the Hubble Space Telescope, which is above the atmosphere, then you can see out to plus 30. And so this is basically a way of thinking about how you can see things and what you can see naked eye and how bright they appear in magnitudes. And so we get this new magnitude scale. So we have the faintest stars are set as 6th, and the brightest stars now end up with apparent magnitude of around 0. Like I say, the Sirius is the brightest, and that's minus 1.4. Magnitude of Venus is about minus 4, the full moon is about minus 12, and the sun is about minus 27. And if you've got a small telescope, you can see out to about 10th magnitude. If you've got a large telescope, you can see out to 30th magnitude. This will become important later for thinking about what things we can see at what distances. And this is just an example of a constellation. This is the Pleiades. Apologies for the pixelation. And you can see you'd easily be able to see this one. This one's a middling brightness. This one's not too bad. And you'd be able to see this, but this would be very faint. These stars around here, you wouldn't be able to see at all naked eye because they have a number above 6. Likewise with this. This one would be a very, very faint star that you could just about make out. And so you get the idea of what the magnitude means in terms of being able to actually see these things. And that's it for understanding apparent brightnesses, and we'll come back to how we make use of this